Information theory lets us quantify the information content of the events. In this theory, unlikely events carry more information than the likely ones. We quantify this intuition using self-information. When we use the natural logarithm for quantifying the information, it is measured in nats. If we were to use the base 2 logarithm, we would measure the self-information in bits, or Shannons. Let's now see how the self-information formula follows the described intuition. As we can see on the right graph, an event with probability 1 has 0 information content. And as the probability of an event approaches 0, it carries more and more information. For example, if we have an unfair coin A that has 0.9 probability of displaying heads when tossed, an event of displaying heads would only carry 0.1 nats of information. However, an event where the coin displays tails carries 2.3 nats of information. Let's now see how we can quantify the information content of an entire probability distribution. With Shannon entropy, we can find the expected amount of information in an entire probability distribution. When we are dealing with continuous cases, Shannon entropy is referred to as a differential entropy. Let's now find the Shannon entropy for the unfair coin discussed earlier. We already found the self-information of events on the previous slide, and we know the probabilities of both events. We can just plug everything we know into the formula, and find that the Shannon entropy for the probability distribution of the coin A is 0.32. To better understand the essence of Shannon entropy, we need to compare what we just obtained with the entropy of a fair coin. A fair coin has 0.5 probability of displaying either heads or tails, and self-information of 0.69 nats for both events. This makes a Shannon entropy of 0.7. As we see, there is more expected amount of information in the probability distribution of a fair coin. This is because an unfair coin A will more often display heads, making it more deterministic. Probability distributions with more uncertainty have higher value of Shannon entropy. Let's now see how can we compare the difference between these distributions. With Kullback-Leibler divergence, we can measure the difference between the two probability distributions. Let's measure the difference between the probability distributions for the two coins we discussed earlier. By plugging everything we already know into the formula for KL divergence, we find that the difference between the two distributions A and B is 0.37 nats. However, when working with KL divergence, we should be aware that it is an asymmetric operation. We will next illustrate this phenomenon. On the previous slide, we found the difference between the probability distributions between A and B. However, it is not equal the difference between the probability distributions between the B and A. KL divergence is an asymmetric operation. We see that finding the KL divergence for B and A results in 0.51 nats, which is different from finding the KL divergence between A and B.